Hey, this is Mr. Ariel, and I'm here today with another video for chemistry. This time it's about solutions and solubility, and I think you learned a lot about this in a physical science class somewhere in your past. So it could be some review, but it's probably been a few years since you've learned some of this, so pay attention as we go along. Now, the most important thing I could tell you about this unit is that it involves lots of words that start with the letter S. You can see 4 of them right here on the page: solubility, solute, solvent, and solution. Lots of students get tripped up over these words, so let's review them now. First up, solubility is a measurement of how much solute can dissolve. In other words, it's the ability of a solute to dissolve. Maybe you could call it dissolvability. Different substances will have different solubility, and we'll come back to this idea in a few minutes. Now next up is solute, and that's the substance that is dissolved into another substance. For example, let's take a picture of lemonade. Now, you know in that lemonade, there is both lemon juice and sugar, which means that both of those are solutes. Solutes are the part of a solution that is present in the smallest amount. And that's certainly true in our lemonade. There's certainly a lot more water in the solution than there is sugar and lemon juice. Now, last thing on solutes, it's important to note that there can be more than one solute in a solution. Because again, solutes are the smaller part of a solution, you can have a lot of them. Now, next up on our list is solvent, and that's the substance that dissolves the solute. In our lemonade example, water is the solvent, and that's because it dissolves the lemon juice and the sugar. Now, the last thing on our vocabulary is solution, and that's the term we use for the entire homogeneous mixture. In other words, for our example, it's everything. All of the solute, all of the solvent mixed together is the solution. Now, water is the solvent in our lemonade example, but water is often going to be the thing that forms a solution, because water is cheap, it's easy to obtain, and it has a property that lets it dissolve lots and lots of different substances. Now, when water is the solvent, the solutions are described as aqueous. That's definitely a term you need to know. Let me slide my notes up. Now, water is such a good solvent that a lot of times it's referred to as the universal solvent. Universal is in quotes because it can't really dissolve every substance on Earth, but it does dissolve an awful lot of them. And that's because water is a polar molecule. Reaching back to a unit from a long time ago, we learned about electronegativity. That's an atom's ability to attract electrons to itself, and the electronegativity of oxygen is higher than hydrogen. That means when hydrogen and oxygen form bonds to make water, the electrons are not shared equally. Instead, the electrons spend more time around oxygen, giving it these partially negative ends to the molecule. It's abbreviated with a little symbol. Let me draw it a little bit bigger, like that, with a little minus. It means partially negative. Now, if those electrons are spending a lot of time around oxygen, that means the hydrogen end of the molecule is partially positive. So what does all this mean? Well, if I add a crystal of table salt, like this, it's a tightly arranged set of sodium and chlorine ions. They're bound together by ionic bonds. And if you dissolve this crystal into water, water molecules will surround it just like this, but they're going to do so in a way where the negative ends are all attracted to the positive sodiums, and the positive end of the water molecule will all be attracted to the chlorines because they're negative. We finish those two molecules up. And when enough water molecules get in, they'll start breaking the bonds between the sodium and the chlorine, and they'll pull it off to the side, and it's dissolved now. Same thing for the chlorine. It'll get surrounded by water molecules and broken off of the main crystal, and so we call that dissolving. Dissolving is what we call it in everyday language. In chemistry, it's sometimes called dissolution, and the ions can be described as solvated. Again, in everyday speech, we'd probably call that dissolved. Now, moving on with the notes, when an ionic substance like sodium chloride dissolves in water, those ions can float around in solution. This will allow the solution to conduct electricity. And we have a name for that. Solutions that can conduct electricity are called electrolytes. This can be tested with a conductivity tester. It's right here on your notes. There's a solution of electrolytes in the beaker because the current can flow from one end of the probe to the next. And so the light bulb will light up. On the other hand, non-ionic substances will not form ions, and when they dissolve, they will not conduct electricity because they stay together in one large piece. Here's an example over here. It's a sugar molecule, and you can see the water molecules attracted to it, but it's too large to break apart, and the bonds holding the molecule together are too strong to break apart, in the way that ions can. So we refer to these substances as non-electrolytes because they don't conduct electricity. Now, the most important idea to get here in your notes is electrolytes. Those are made of ionic substances, and so that's going to be a metal plus a nonmetal. And we learned that a long time ago in this class. And then non-electrolytes are going to be covalent substances. And so that's going to be two or more nonmetals. So make sure you've got all that into your notes, and then let's move on. Now, moving into some more ideas about solubility, remember that term means dissolvability. We have several factors that will affect how well something will dissolve. First up is the nature of the solute and solvent. Your note sheet says like dissolves like, but what I want you to add in is that polar solutes will dissolve in polar solvents, and also nonpolar solutes will dissolve in nonpolar solvents. That's like dissolves like. Now, we already discussed table salt dissolving in water, and that was a polar solute in a polar solvent. We had lots of little charges that allowed the water to be able to pull those ions off the crystal. Now, an example of nonpolar dissolving would be something like grease and oil. If you get grease or oil onto your hands, I'm pretty sure you know that water alone will not wash it off. And that's because the entire grease molecule is nonpolar, while water, on the other hand, is polar. And so water won't dissolve the grease. Now, soap, on the other hand, well, part of soap is nonpolar, and so it can mix with the grease and dissolve it, but then the other side of the molecule is polar. And so when you use soap to wash your hands, it both attaches to the grease and pulls it off of your skin, but then it can also mix with water so that it can then be washed off of your hands completely. Now, moving on, another factor that affects solubility is temperature. Higher temperatures will increase the solubility of a solid. If you think about it, the solute and solvent, they all move faster at higher temperatures. I mean, the little particles inside of them. So this means that substances will dissolve faster at higher temperatures. On the other hand, increasing the temperature of a solution will decrease the solubility of gases. In other words, gases dissolve best at low temperature. Add these two examples into your notes somewhere. First, that sweet tea is usually made with hot water, as the sugar won't dissolve if you try to mix it up with cold water. And for the gas solubility that it decreases at cold temperatures, you probably know that a warm soda will go flat quicker than a cold one. If you open a warm soda and drink it, it'll seem incredibly fizzy, and that's because the gas is less soluble at that warm temperature. That also explains why if you open a soda while it's warm, and then you put it in the refrigerator, it's always going to seem a little more flat than one that you cooled before you opened it. Gases just aren't real soluble at warmer temperatures. Now, moving on with the other factors that affect solubility, pressure is the last thing to consider. Pressure only affects the solubility of gases, and increases in pressure will increase the solubility of a gas. If you think about a soda being put into a bottle at the factory, they're going to bottle it at high pressure, and at that high pressure, that forces the carbon dioxide into the solution. Opening the bottle later will lower the pressure, and you immediately see the fizz of bubbles where the carbon dioxide is coming out of solution. Now, we're going to skip over Henry's law, and let's move on with the last part of the notes. Now, for rates of solution, there are three things that you can do to increase the rate at which a solute will dissolve. First, you can stir, shake, or agitate the solution. That just means you physically mix it up, and it causes the particles to shake around and dissolve faster. Second, you can increase the temperature, but that only works for solids. Remember, that's going to decrease the solubility of gases. And last, you can use smaller particles, like you can grind up sugar into a powder, and it will dissolve much faster than using bigger cubes of sugar. Now, the last thing we need to pick up in the notes is the types of saturation. A saturated solution occurs when the maximum amount of solute that's possible is dissolved in the liquid. Now, this is going to show up as a line on a graph where we have grams of solute per 100 milliliters of water, and we have temperature on the x-axis. So again, this line right here represents a saturated solution. And we'll get some practice working with this kind of a graph in just a minute. So you can see this line, it curves upward at high temperatures, and that's because the solubility of most solids will increase as the temperature increases. Now, anywhere under the line is an unsaturated solution, and that's a solution where you haven't yet dissolved all of the solute. In other words, there's more that you could dissolve into the solution. And then anywhere above the line is supersaturated. and that means there's more solute than is theoretically possible at that temperature. Now let's move on into the I do, we do problems. Now for these, you're going to see a lot of these solubility graphs like the one at the top of the screen, and they often have a lot of lines on them, and you're going to learn to filter out the ones you don't need. Like for the first problem, we want to know the solubility of KClO3 in 100 grams of water at 90 degrees Celsius. Now the y-axis says we have grams of solute per 100 milliliters of water, but the density of water is 1 gram per milliliter, and so this 100 milliliters of water is the same thing as 100 grams of water. Now to find the solubility of KClO3 at 90 degrees Celsius, the first thing we're going to do is find 90 degrees on the x-axis. And then my KClO3 line is right here, and so I'm going to carefully move up to that line just like this. And then to finish it out, we're going to read the number of grams by coming across to the y-axis. And I think that's somewhere around 53 grams, and there's room for error there. You might say it's 54 or 52, and we're all going to be okay with that answer. Now for B, at what temperature is the solubility of KClO3? Is it going to be 20 grams in 100 grams of water? Well, let me clean up my graph. I'm still focused on this line right here, but I want to know about this 20 grams. What temperature will 20 grams dissolve? So I'll come right here to 20, and then I'm going to come across until I meet that line right here, and I'm going to drop straight down. And that's about 50 degrees. Again, you might say it's 49 or 51, and that's going to be fine. For C, we want to know how much of this substance will dissolve in 350 grams of water at 40 degrees C. So let me clean up my graph real quick. So I'll start here, and I'm going to move up to that potassium chlorate line and come straight across. Now I'm going to say that's 16 grams, and that was over 100 grams of water. And so we can just turn that into a conversion problem and say we have 350 grams of water, and we can just put that over 1. And both of those units will cancel out, and so we can just finish that math on a calculator, and when you do that, that's going to get you 56 grams of KClO3. You might realize that what we just did is multiply 16 by 3.5, because 350 grams of water is 3.5 times 100 grams of water. And that's what our math shows below. Now moving on. All right, for the next one, we want to know the solubility of KNO3. That's this line right here. We want to know how much of it will dissolve at 60 degrees C. So I'm going to start on the 60 degrees temperature. I'm going to go until I meet that line. Looks like it's right about here. And I'll come across to read that temperature. Now I'm going to estimate that's about 108 grams. Again, there's room for error. Now for B, we want the temperature where the solubility is 20 grams. Let me clean up my graph. And for this one, we want to start at 20 grams. We want to come across until we meet that line, but that is actually right there. And so we're going to drop straight down. And I'm going to estimate that's about 5 or 6 degrees. Now for C, we want to know how much KNO3 will dissolve in 220 grams of water at 60 degrees C. Now we already know the solubility of the substance at 60 degrees, and so I'm just going to use that information here. That's 108 grams of KNO3 per 100 grams of water. It's like a ratio, but we want to know how much will dissolve in 220 grams of water. We can put that over 1, and so those units cancel out. And when you multiply that together, that works out to be 237.6 grams of KNO3. All right, we've got one more problem to go. We have a saturated solution of NH4Cl. Let me go ahead and go back to my graph and clean that up, because NH4Cl is this line, and we have it at 90 degrees, and it's being cooled to 50 degrees. And so we want to know how much of the solid will not stay dissolved. Well, let's read the graph. At 90 degrees, let me come up and find that solubility. We're going to come straight across. I'm going to estimate that at 90 degrees, that's 72 grams will dissolve. I think your paper right here says 100 gram solution. So that's 72 grams in 100 grams of water. And then we're cooling it down to 50 degrees. So we're going to come back to the graph. We're going to go to 50, go straight up until we meet that line again. And remember, solids usually dissolve less well at cooler temperatures. And it looks like there, that's around, let's say, 53 grams per 100 grams of water. And so for this, we can just subtract those two solutes. And 72 minus 53, that works out to be 19 grams of NH4Cl will not dissolve. All right, now that's it for this set of notes and problems. I hope this video has been helpful to you today. And as always, thanks for watching.